In this video, we are going to dive into cubic functions, which is a part of our calculus section. In the past, we've looked at parabolas, so those were x to the power of 2. But if you have a function like this that looks like it has 2 turning points, okay, then it's a cubic function, so x to the power of 3. And thanks to calculus, we actually know quite a bit about functions like this. So over here, we've got a very simple cubic function, and I've just highlighted a number of things. So over here, in yellow, we've got our plain old x-intercepts, okay? And how do we work out an x-intercept of a graph? We let y equal 0. Okay, so that remains the same. We can still work out the x-intercepts, even though this will be an x to the power of 3 equation that we are given. Okay, then over here in this red color, we've got a y-intercept. And how do we work out a y-intercept? We let x equal 0. So if they give me the equation, I should be able to work out x and y intercepts. Just a note here is that you're going to need to have either synthetic division or long division to work with this. But we'll get there, we'll do some examples, and I hope it'll come flooding back to you, that factor and remainder theorem knowledge that your teacher should have given you. Okay, then we've got what we like to call stationary points. Okay, you can still call them turning points if you want to, but they are officially known as stationary points, and that's a point where the graph changes. So here it's increasing, it hits the stationary point, it's neither increasing nor decreasing there, and then it changes direction and it starts decreasing until it hits the next stationary point, and then it starts increasing again. Okay, now these stationary points can form local maximums and local minimums. So this one in particular is the local minimum, and then the one in the top there is going to be the local maximum. Okay, how do we use calculus to work out turning points of a cubic function? That's what I'm really interested in. At the stationary points, the derivative, the first derivative of x is equal to 0. So that's very important. If you are asked to work out stationary points, that's going to be your approach. You're going to differentiate, and then you're going to set it equal to 0. Now over here, we've got another point, and that's known as a point of inflection. Okay, and at a point of inflection, our second derivative is equal to 0. But what exactly is happening there at a point of inflection? Well, we've got this new concept now that we've got cubic functions, and we look at the shape that the graph makes. So here, you'll see it's making a little cave, and that cave is facing downwards. So we call this concave down. And then once it hits the point of inflection, then the concavity changes, and then this part here becomes concave up. Okay, so at the point of inflection, things change. And the second derivative is what tells us whether or not something is going to be concave up or concave down. So if our second derivative is going to be negative, then it's concave down. And if our second derivative is positive, then it's concave up. Okay, so there's loads of theory squashed into a cubic function, but if you have a basic understanding, you'll be fine. So whenever I'm asked to draw a cubic function, I start and I say I can get x-intercepts by letting y equal 0. I can get y-intercepts by letting x equal 0. I can get stationary points by using the first derivative, and I can determine inflection and concavity by using the second derivative. So let's have a look at an example and put this knowledge to the test. So here we are given the question, sketch the graph of f of x is equal to x cubed minus 3x squared plus 4. So in the past, I've been able to identify, is it a hyperbola, is it a parabola, all those things. Now, the minute I see to the power of 3, I need to start thinking cubic function, and I'm going to use calculus. Okay, and I've got a little checklist for us. So up here in the corner, we've got all the things we need to look out for. First up, the x-intercepts. How do we get an x-intercept? We let y equal 0. So that's where we're going to start, and we're going to say 0 is equal to x cubed minus 3x squared plus 4. But what I notice here is there is no x term. Okay, so be careful there. It goes from x squared and then down just to plus 4. So in order to make sure that I don't make any mistakes, I like to just remind myself that there's another term in there. You don't have to do that, but it's definitely helped me to remember 3, 2, 1 needs to be my powers of x there. Right, so looking at it straight off the bat, we can see we don't know how to factorize this. So we need to go and find a factor. Okay, and we do that by substituting into this equation. I always start by substituting in 1. You could start by substituting in 0, but you'll end up with this answer here of 4. You can see it straight away. So that's not going to work. Our goal is to end up with an answer of 0 for the whole thing. So let's work out f of 1. So everywhere I see an x, I'm going to substitute in a 1 squared over there. Okay, so that's 1 minus 3 plus 4. And that ends up being 2, which is not equal to 0. So that doesn't help us. Okay, then the next thing I'll try is minus 1. And you're literally just going to keep going until you find a factor that's going to work for you here. So let's see, that's going to give us minus 1 minus, because look at this, minus times a minus is going to be a plus. That's going to end up being then a minus 3 plus 4, and that does equal 0. So there we have it. We have found, which is great, a factor that would work. All right, so what we can do then is we can say, well, this now is going to look something like this. 0 equals, okay, so I know that x equals minus 1. If I want to take it back into the brackets, I need to move that over. So this is going to be x plus 1 and then some more things. Okay, but I'm not ready to do that yet. I'm going to need to do some synthetic division. Okay, this is how synthetic division works. We take all of the coefficients here. So we've got 1 minus 3, 0, don't forget about that, and then 4. And we are going to divide. So let's see, 1 minus 3, 0, and 4. What we do is we take our factor that we found, that minus 1, and we pop it outside. Then we drag down this first number, so 1 moves down. Okay, and then all we need to remember is multiply and add. Okay, so we say minus 1 times 1, that gives me minus 1, and I add it to minus 3, and so minus 1 plus a minus 3 ends up being minus 4. Then I need to multiply and add minus 1 times minus 4, that gives me positive 4, add it to the 0, that's going to give me positive 4. And then I multiply and add. Minus 1 times 4 is going to give me minus 4, and I add it there, and that gives me 0. If I get a 0 here at the end, I'm happy, because that means I have factorized this correctly. So these three things now become the coefficient of my second bracket. So this second bracket is 1x squared minus 4x plus 4. Okay, so we found a factor bracket. There it is. And then we used synthetic division. You can also use long division. There are loads of little summaries out there that you can go and check out. But we used synthetic division to work out the coefficients there. And now we're unstoppable. We can factorize that. That's just a plain old trinomial. So x plus 1 is in the one bracket. And then we'll have two more brackets. X times x is x squared. Factors of 4 are 2 times 2. And to get a minus 4, we'll say minus 2 minus 2. So therefore, x is equal to minus 1, or x is equal to 2, and that's actually going to be twice. Okay, and there's something significant about getting the same answer, but we'll see it soon enough. All right, so those are our x-intercepts. Tick. Okay, y-intercept is very straightforward. So y-intercept, we let x equal 0, and so that's just going to equal 4 there. Tick for y-intercept. Okay, stationary points, we get those by getting our first derivative and letting it equal to 0. So let's differentiate then. Here's f of x. So f prime of x is going to be, we're going to take this 3 down. 3 times 1 is 3. x, and then we subtract. So it's 3x to the 2, and then minus 2 times 3 there is 6x to the 2 minus 1, and then the derivative of a constant is just 0. Okay, so there we have our derivative, and where the derivative is equal to 0, that's where I have stationary points. So I'm then going to say, okay, well, let's let this equal to 0. 3x squared minus 6x, and this is easy to solve. It's just a square. There's not the cubic situation that we had there. So we can start by taking out a common factor. So 3x, and we are left with x minus 2. Okay, so I've got two options here. Either 3x equals 0 or x minus 2 equals 0. And so I've got two stationary points at 0 and at 2. Okay, so tick for stationary points. Or actually, it's only half a tick now, because those are just the x coordinates, and I need a full-on turning point. So I need to substitute them in to get my y values. Okay, so when x is equal to 0, let's work that out. F of 0 is equal to, and remember, always go back to the original equation here. Okay, so f of 0 is then equal to, oh, that's easy, 4, because all those x's, 0, 0, that just stays 0. So there's my first turning point. I can write it as 0 and 4. So it's going to turn on the y-intercept. And then at x equals 2, let's substitute that in. Okay, and I can see there, have a look at this, grade 12s, you're going to see things coming together. Okay, what happens when x equals 2 twice? Okay, so let's substitute that in. F of 2 is equal to 2 to the power of 3 minus 3 times 2 squared plus 4. If you pop that all into your calculator, you're going to get a 0. So that means that the other turning point is at 2 and 0. Okay, and so just a little bit of enrichment. If you get an x coordinate more than once, it means that the graph will actually also have a turning point there at that intercept. So it won't go through, it'll bounce on the axis. Next up on our checklist is this little concept of inflection. Okay, so inflection links to the second derivative. So let's work that out. We've got our first derivative over here, 3x squared minus 6x. So our second derivative, I'm going to work out over here. And that's going to be, take the 2 down, 2 times 3 is 6x to the 2 minus 1, minus, and that one's just going to become 6 because x to the power of 1 is going to multiply by 1 and then subtract. Okay, so there's our second derivative. Okay, we've got a point of inflection when this is equal to 0. So 6x minus 6, take that over. And so we've got a point of inflection at x equals 1. Okay, that's cool. And then we can work out concavity also from this. So if my second derivative, which I've now worked out to be 6x minus 6, if it's smaller than 0, then this is going to be concave down. Okay, so let's work that out. 6x smaller than 6. So for x smaller than 1, it's concave down. And then in the same way, 6x minus 6 is greater than 0, then it's concave up. Okay, we are managing to fit all of this info in here. That's great. So x greater than 1. Okay, so checklist is done. I've got my intercepts. I've got stationary points. Don't forget, like I nearly did, to also get y values for your stationary points by substituting in your x coordinates into the original f of x. And then you get inflection by working out your second derivative, okay? And you've got to do 3 steps here. Second derivative equals to 0, that gives you the point of inflection. And then to work out concavity, if it's smaller than 0, it's concave down. And if it's greater than 0, it's concave up. So we are ready to sketch. Now, most of the times we're dealing with really big numbers, so we're not always expected to draw this exactly to scale, but we still want to be accurate. Okay, so we've got 2 x-intercepts. We've got an x-intercept at x equals minus 1 and another one at x equals 2. Then we've got a y-intercept, we said at 4. Okay, And then we've got some turning points, and we happen to see that our stationary points were actually exactly at our intercepts. Okay, this doesn't happen very often, but this is a nice little question for us. So 0 and 4 is already there, and 2 and 0 is there. So let's just make a note for ourselves there that those are also going to be turning points. Okay, and then we got all this inflection stuff. So let's first of all plot our inflection point, which is at x equals 1. So somewhere, let's give ourselves a little dotted line there. Somewhere on this line, we are going to hit our inflection point, and it's going to be concave up, everything smaller than that. So in other words, it's going to be like this. And once it hits that point, it's going to be concave down. Okay, and then we're ready to draw. So we're going to sketch. Don't stop on the intercept. Start a little bit ahead of it. Okay, going through there. Bounces on the axis. Remember that was also a turning point. And there we have the graph of f. Great job, grade 12s. Remember this little checklist if ever you are asked to sketch a cubic function.